entitled A Deductive Verification Framework for Circuit Building Quantum Programs. Christophe, the floor is yours.
Okay. Okay, thank you, Michel. Do you hear me and do you see my screen?
Yes, I can hear you.
Okay, so hello everybody. I'm Christophe from CEA in Paris, in France, and I'm going to present our work about the formal verification of quantum programs. So it is a work that was presented at ESOP this year. To start, just a brief view on the history of quantum computing. So we can date back the history of quantum computing from 1982 is the Richard Feynman intuition that something could be made using the storing of information in the state of quantum matter. And since then, there has been 40 years basically of paper history. That is a progression of descriptions of algorithms on the paper. And more recently, in the last 20 years, in parallel to that, there is a starting history of growing in power propositions of prototypes of physical implementations of quantum machines, of these algorithms. And the interesting thing is that right now, these prototypes are reaching the critical size from which they are able to perform some tasks that are not possible for classical computers. So we talk about quantum supremacy, and basically it is the entering of the era of quantum computing relevance. We can say that way. So we think that it is time for investing and questioning about software engineering in the quantum field. So shortly, what we manipulate in quantum computing is a quantum circuit. And here I just want to highlight the very simple modular structure of this quantum circuits. So we start with a recursive set of elementary operations that are called the quantum gates. And then we can compose them by two kinds of composition, either in sequence or in parallel. And there is this matrix semantics interpretations that assign to each elementary operation a matrix and then composes sequentially with the matrix products and in parallel with the Kronecker product. Now, the standard architecture model for quantum computing is actually an hybrid model where the control of an execution is performed by actually a classical computer. So this classical computer executes a program, and sometimes punctually it has a specific computing request that it delegates to a quantum coprocessor called the QRAM. And this special computing request is the quantum circuits that we just saw before. So this is for the model of architecture. And now, thanks to that, we want to implement algorithms. And here I highlight this is a screenshot of the description of the short order finding algorithm from the Nielsen-Armstrong manual. So we can consider it as the most representative quantum algorithm in the reference manual. So something that is very general. What I want to observe on this screenshot is that in the presentation of this algorithm, the procedure it describes is preceded by a specification preamble. And in this specification preamble, we have the declaration of some parameters with some preconditions over these parameters, constraints that they must satisfy. So input parameters and post conditions, conditions that the implementation should satisfy, that concerns two kinds of specification. First, telling about the functional correctness, what we expect from the implementation of this algorithm, and the other one telling about the complexity, that is basically the number of elementary operations that we need to perform to execute this algorithm. So two things I want to highlight. First, the algorithm is parameterized by a set of constraints, preconditions, parameters. And second, the specifications, both functional and in terms of complexity, here is a full wide part of the algorithm itself. Then, when we are going to implement this kind of algorithm, we are writing a program that takes in input the parameters of the algorithm, and in function of these parameters, outputs a quantum circuit. And so for the implementation to be correct, the produced circuit should meet the specification for any possible value of the entry parameters. So there is a kind of higher level view in this paradigm of quantum programming, because what we are writing are programs that takes input parameters and produce as output circuits, and then each instance of the circuit behaves itself as a function manipulating quantum data. So we have to check that the circuit should meet the specifications for any possible value of the parameters. And it's particularly maybe tricky because quantum programming is by many ways non-intuitive. So there is a high risk for bugs. So how are we going to validate these quantum programs and ensure that they meet their specifications? Just a word about the classical strategy of testing. It happens to be very difficult to handle actually in the quantum case for different reasons. Maybe the two main ones are that first, there is no means to control a quantum execution. I mean, it's not possible to insert assertions or tests within the execution to verify something and then to restart the execution because, of course, of the destructive measurements. And in addition to that, testing is expensive and often statistical. So if you want to use a testing strategy, you will have to launch a set of tests that should be large enough to build a statistical distribution. So to overcome these weaknesses of testing strategies, there are some recent works developing methodology for assertion checking, but we think that they still raise unsolved questions concerning, in particular, the scalability of the method and a clear methodology to treat oracles. So what we propose is to use full verification, formal verification, because it brings several advantages. In particular, there is no need to execute the program, so we don't face the control and destructive measurement problems. And in addition to that, we can manage unbounded state spaces and provide what's for all an absolute guarantee of the correctness of a program. So the challenges in this purpose are mainly twofold. First, to handle the higher level programming paradigm that I described before, with functions producing circuits and circuits themselves behaving as a function. And the other thing is to handle the non-standard theory framework of quantum computing, including probabilities, complex number, Kronecker products, and so on. In addition to that, so we want to be able to handle parametric programming. We want to automate the proof support as far as possible. And we want to be able to handle the complexity specifications in addition to the functional ones. And so we are following a deductive verification approach. Just a brief look at the state of the art in this domain. And I just want to highlight something. That is that there seems to be a trade-off to make in the existing propositions between the handling of parametrized circuits and the proof automation. So the main challenge in our development of a tool which is called Qbricks is to propose a unique environment that handles both the parametrization and some proof automation. And we do that by developing some first-order reasoning techniques about quantum programs and an adequate set of deduction rules. So basically what we developed is a programming language, so Qbricks DSL, together with a specification language and a proof framework, which is an OR logic adapted to Qbricks. All this material enable to describe the behavior of parametrized circuits with first-order formulas, first-order proof obligations. This is made possible thanks to the flexible symbolic representation that we developed, which is called parametrized pattern that we are going to see on the coming slides. And in addition to that, we provide dedicated mathematical libraries, including all the mathematical material that is necessary for quantum computing. And this enabled us to implement and formally verify some non-trivial case studies, and in particular, the short-order finding algorithm. So schematically, in Qbricks, we write some code together with its specification. The code is interpreted via a circuit semantics. Then we use our deduction logic or our style logic to generate from the specification some first order proof obligations. Since the tool is embedded in the tool Y3, then these first order proof obligations are directly accessible, and to support them, we can either call to a set of SMT solvers or enter manually some interactive commands to ease the work of the solver. So a brief word about the language itself, the way we build the circuits. What I want to underline here is that we start from a very simple set of operations. So we have some elementary gates, and we have the two relations of composition, parallel and sequence. And in addition to that, we have a constructor for the creation and annihilation of ancilla qubits. So a very restricted set of primary operators, and on top of them, we derive some higher level combinators like the inversion of circuits, the control, the qubit permutations, and so on. Another important aspect of the language is that iterations are restricted to bounded case, which means that we can iterate a function only a finite number of times. This is important for the first order reasoning framework. Now, concerning the semantics for parametrized circuits, so the standard is to use the matrix semantics, but it happens to be quite difficult to handle and to manipulate formally. And in addition to that, if we look at how the semantics of a circuit is described in the algorithm, we don't see matrices, but kinds of sums of vectors. And these kinds of sums of vectors have been formalized recently by Matrieni through the path-sum formalism. So basically, the observation is that for any quantum circuit and any input computational basis state, applying this circuit to the state results in a quantum state having this general form. And so this general form is a sum of elements bounded by here a red integer parameter, and each element of the sum is a complex index coefficient determined by this blue function and an element of the computational basis given by this green function here. And it happens that each element, the red, the blue, and the green, has a modular recursive definition over the structure of the surface. So the representation is concise in practice. It has good compositional properties, but in this state, it doesn't handle parametricity. So we generalized this path-sum semantics by integrating the parameters of circuits within each element of the path-sum, and by deriving first order modular rules, enabling to work with the red, the blue, and the green function, depending on the structure of a quantum circuit. And it enabled to reduce the semantics of a family of quantum circuits to this simple first order modular reasoning rule. This is at use both for the writing of the specification and for the deduction, of course. One look at our dedicated mathematical libraries. So basically, it is over 14,000 lines of code long. There is some linear algebra, some binary arithmetics, complex number theories, Kronecker product, unity circle, and so on. And all these libraries are freely available and developed in Y3, so available for any other future purpose. Now I'm having a little look at the way we write a program we use Qbricks. So we come back to the description of algorithm. So again, the algorithm is composed first by the specification preamble, declaring the input parameters, and the specification, the post conditions, functional and in terms of complexity. And in addition to that, we have the body of the algorithm itself, which is made by a sequence of quantum operations, and in parallel, a sequence of intermediate assertions describing the state of the system in a format that looks like the Python. So in our deductive verification approach, actually, we could directly translate into the code this particular scheme of quantum algorithm. So in Kubrix, we write functions. It is a functional programming, taking as input the parameters of an algorithm and outputting quantum circuits that are composed by the sequence and parallel relation of composition. So we write this functional programming, and in addition to that, in the code itself, we write the specification of this code. So the preconditions for the parameters and the post conditions, both concerning the complexity of the implementation and its functional behavior. So the code plus the specifications, and at the compilation, thanks to the embedding in the Y3 tool, the specifications generate proof obligations that are first order formulas. And we can prove the satisfaction of these formulas in a context through the Y3 interface, either by directly calling SLT solvers, or if it is too difficult, by entering manually a number of interactive commands. And so to support the proof of the specification. So this is for the general methods of Qbricks. We probed it against complex case studies, but I will tell more in the coming slides. So that's this point. So the experimental evaluation, we apply the methods to a number of case studies, in particular the short order finding algorithm. So here are some data about the implementations, the number of the length of the implementation together with the specifications, the number of generated proof obligations, the weight of automation of the PO's verification, and the number of interactive commands I had to enter to finish the proofs. Maybe the most interesting column is this one, the weight of automation. We see that it is quite stable along the different case studies, and in particular for short order finding, it is over 95%. Some elements of comparison in these case studies with regards to the rest of the literature. So first, about the complexity of the case studies. These 4 bars indicates the case studies that we have in common with the rest of the literature. So there is a typo. It's not only QFT, but this for one, the CHOSA, QFT, Gruber, and QPO here. And yes, the short order finding implementation represents basically a times 6 gap in terms of complexity, measured by the length of the code itself together with the specification. So more complex case studies and further automation, which is illustrated by this diagram. So we have a set number of case studies in common with the rest of the literature. So we could compare the complexity of the proofs, and I measured it there by the data of the number of lines of specifications added to the number of proof commands to finish the proofs. And basically, Kubrix brings a factor 3 improvement with this measure concerning the human required proof effort. So, in conclusion, we have a framework for formally verified circuit building quantum programs featuring both parametricity and automation. Thanks to that, we could develop, implement, and verify non-trivial case studies, and in particular, the first ever verified implementation of the short order finding algorithm. we developed parametrized path-sum as a tool of choice for quantum verification. And this also brought a set of quantum-oriented mathematical libraries available in Web3. The material is freely available online at this address, and the development of Qbricks opened many exciting perspectives, including works in compilation, development of higher level verified language, development of NISQ application, and so on. So to take the challenge, we are hiring a PhD and a postdoc, and you can contact either me or Sébastien Bardin if you are interested. I thank you for your attention, and I'm available to answer your questions.
Thank you very much.